Your planet is so small that more than 1 million copies of it could fit inside the sun. That sun is just one star out of 400 billion stars, moving through a galaxy so wide that light needs 100,000 years to cross it. None of that prepares you for what is right next door. Only 2.5 million light years away, a galaxy named Andromeda, 220,000 light years across, about 1 trillion stars inside it. It is bigger than everything you call home, and right now, it is moving straight toward us. What follows is a journey through real distances, measured distances. They will break every intuition your brain has about size, about space, and about where you actually stand in the universe. No guessing, no magic, just science. You think you know how big Earth is? You have seen the photos from orbit, the curved blue horizon from the International Space Station. You may have flown across an ocean and felt somewhere around the 6th or 7th hour of staring out that small oval window, a growing sense that this planet is truly enormous. By every standard your body and brain evolved to handle, you are right. Earth is incredibly large compared to a human. But that feeling, that deep sense of planetary hugeness, is the first thing we must take apart. Because once you start measuring Earth against the things around it in space, something uncomfortable happens. The planet under your feet, the world that holds every city, every ocean, every mountain range, every war, and every civilization that ever existed, begins to shrink. And it never stops shrinking. Start with something you can measure. The circumference of Earth at the equator is about 24,900 miles. That is a real number, verified. You can check it with GPS satellites and geodetic surveys. But real numbers and numbers you can truly understand are not the same. So let us make it physical. If you got on a passenger jet flying at 550 miles per hour and never landed, never stopped for fuel, never turned aside for weather, it would take you just over 45 hours to circle the planet. Nearly 2 full days of non-stop flight just to return to your starting point. If you tried the same trip in a car going 70 miles per hour on a perfectly straight highway wrapped around the equator, the drive would take about 14.5 days. 2 full weeks of driving without rest, without sleep, without stopping for gas, just to trace the outline of the planet you were born on. That is Earth at human speed. It feels huge because for a species that spent most of its evolutionary history walking at 3 miles per hour across African grasslands, it really is huge. Your legs were never built for this planet full circumference. Your intuition was calibrated for river crossings and seasonal moves, not for continental distances. When early humans walked out of Africa about 70,000 years ago, the journey to the southern tip of South America took about 10,000 years of slow generational migration. 10,000 years to cross what was, from the planet point of view, just a fraction of its surface. Earth was built on a scale that dwarfed every biological system that ever evolved on it. Humans were no exception. Now go vertical. The deepest point in any ocean is the Challenger Deep in the Mariana Trench, in the Western Pacific. It goes down about 36,000 feet, nearly 7 miles straight down. At that depth, water pressure exceeds 16,000 pounds per square inch. That is about 1,000 times the atmospheric pressure you feel at sea level. The temperature is just a few degrees above freezing. Sunlight disappears completely within the first 1,000 feet. Below that, the ocean is in total permanent darkness. Fewer than 30 people in all of human history have ever reached the bottom. Each descent required custom-built submersibles with titanium pressure hulls built to survive forces that would crush a nuclear submarine like an aluminum can. It sounds like a trip to another world. In terms of pressure, darkness, and cold, it might as well be. But here's the number that changes everything. Earth diameter is about 7,918 miles. The Mariana Trench, the single deepest scar on our planet's surface, is a scratch less than 7 miles deep on a sphere nearly 8,000 miles across. To make this physical, if you shrank Earth to the size of a standard basketball, the Mariana Trench would not even be detectable by a human fingertip. You could run your hand across that whole basketball. The deepest point in the ocean would feel like nothing. Perfectly smooth, impossible to feel. The feature that required custom engineering and decades of technological development for humans to reach is, at planetary scale, a rounding error. It might as well not exist. This is the first lesson in cosmic scaling. Things you think are huge often become immeasurably small when you zoom out just one level. The Mariana Trench defeats human engineering. It challenges human survival. It is a real frontier. But to the planet itself, it is a scratch too shallow to notice. Remember this pattern. It will repeat at every scale we see from now on. Each time it repeats, the thing that just felt enormous will become invisible. And we have not even left the planet yet. Earth orbits the Sun at about 93 million miles. Astronomers call this distance 1 astronomical unit. It is the baseline for measuring everything else in the solar system. 93 million miles. Let us make that number mean something to a human body. At the speed of a commercial airplane, that trip would take over 19 years of continuous flight. 19 years in the air without landing. A child born the day you took off would be an adult when you arrived. At the speed of a bullet from a high-powered rifle, about 1,700 miles per hour, you would still need more than 6 years to reach the Sun. 6 years at bullet speed. And even light, the fastest thing in the known universe, moving at about 186,000 miles per second, takes 8 minutes and 20 seconds to go from the Sun's surface to your eyes. Think about what that means in real terms. When you look at the Sun, you are not seeing it as it is right now. You are seeing it as it was over 8 minutes ago. If the Sun suddenly vanished this instant, you would not know for 8 minutes and 20 seconds. You would still feel the warmth. You would still see the light in the sky. You would keep living in complete ignorance of the event for the time it takes to brew a pot of coffee and pour a cup. That is how far away we are from our own star. But distance is only half the story. The Sun itself is a monster of scale that makes Earth look like a speck of dust. The Sun diameter is about 864,000 miles. To put that in direct comparison, the Sun is about 109 times wider than Earth. You could line up 109 Earths side by side, and they would barely stretch across the Sun face from one edge to the other. Its volume is even more crushing. About 1,300,000 Earths could fit inside the Sun. Not next to it, inside it. Every continent, every ocean, every mountain range, every desert, every glacier, every city, copied 1,300,000 times, and the Sun would swallow all of them with room left over. The object you see rising every morning is not a gentle lamp in the sky. It is a sphere of superheated plasma so massive that it holds 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust drifting between the orbits, makes up the remaining 0.14%. Jupiter, the largest planet in our system, which could itself hold over 1,300 Earths inside its volume, is a gravitational footnote next to the Sun. Earth does not even count as a footnote. It is a cosmic speck orbiting a thermonuclear engine that turns about 4 million tons of its own mass into pure energy every single second through nuclear fusion. Let that number sink in. 4 million tons of matter per second. Not per year, not per day, per second. That is the mass equivalent of about 22,000 fully grown blue whales destroyed every tick of the clock. Their matter turned entirely into electromagnetic radiation and neutrinos. And the Sun has been doing this nonstop for about 4.5 billion years. It will keep going for about another 5 billion years before it runs out of hydrogen fuel and starts turning into a red giant star, eventually shedding its outer layers and collapsing into a white dwarf remnant. In cosmic terms, our star is middle-aged, stable, and completely ordinary. It is one of the most common types of stars in the galaxy. It is not especially bright, not especially massive, not especially old. And yet, its scale makes every structure humanity has ever built, every distance humanity has ever traveled, every measurement humanity has ever taken on the surface of this planet feel like a child drawing taped to the wall of a cathedral. Here's where the emptiness starts. Earth sits 93 million miles from the Sun. Mars orbits farther out at about 142 million miles. Jupiter, the first and largest of the gas giants, circles at about 484 million miles. Saturn drifts at 886 million miles. Uranus at about 1.8 billion miles. And Neptune, the farthest recognized major planet, orbits at a staggering 2.8 billion miles from the Sun. That is the span of our solar system measured by the major planetary orbits. nearly 3 billion miles from center to edge. A beam of light leaving the sun takes over 4 hours to reach Neptune. A radio signal sent from mission control on Earth to a spacecraft near Neptune, moving at the absolute speed limit of the universe, takes about 4 hours to arrive. If a spacecraft near Neptune had an emergency and radioed home for instructions, the operators in Houston would not get the distress call for 4 hours. Their reply would take another 4 hours to travel back. 8 hours of round-trip communication delay at the fastest speed physics allows. For all practical purposes, a spacecraft near Neptune operates alone. This isolation is not theoretical. It has been experienced by every deep space mission humanity has ever flown. When NASA New Horizons spacecraft flew past Pluto in July of 2015, its closest approach happened entirely on autopilot. Mission controllers had uploaded the flyby commands hours in advance. Because the one-way signal travel time from Earth to Pluto was over 4.5 hours, there was no chance of real-time guidance, no chance of corrective commands during the encounter. The spacecraft did its observations alone, stored the data on board, and then spent over 15 months slowly sending the results back to Earth at a trickle of about 1 to 2 kilobits per second. The whole data set from a flyby that lasted hours took more than a year to download across the solar system. And Pluto is close compared to the outer edge of the Sun domain. Voyager 1, now more than 15 billion miles from Earth, communicates with a radio transmitter that puts out about 22 watts. That is about the power of a refrigerator light bulb. Its signal spreads out in all directions as it crosses the solar system. By the time it reaches NASA Deep Space Network antennas on Earth, the received power is about 0.00000000001 watts. That is about 10 billion times weaker than the power needed to run a standard digital wristwatch. Engineers have to use cryogenically cooled receivers and hours of signal averaging just to pull intelligible data out of the noise. And Voyager 1 has not even left the Sun gravitational sphere of influence. It is still, by any meaningful definition, inside our solar system. This is what emptiness means in real engineering terms. Not abstract distance on a chart, but the concrete, measurable weakening of every signal, every communication, every link between a human-made object and the civilization that built it, stretched to breaking across voids that exist between objects inside our own tiny stellar neighborhood. But even Neptune is not the true boundary of our solar system. The Sun gravity reaches much farther than the last planet. The Kuiper Belt, a ring of icy bodies beyond Neptune orbit, stretches from about 30 to 50 astronomical units from the Sun. Beyond that lies the scattered disk, and farther still is the hypothesized Oort cloud, a vast spherical shell of icy objects thought to extend from about 2,000 to as far as 100,000 astronomical units from the Sun. 100,000 astronomical units is about 1.6 light-years. The full gravitational domain of our single, unremarkable middle-aged star stretches across a sphere maybe 2 to 3 light-years across. 1 light-year is about 5.88 trillion miles. The Sun's sphere of gravitational influence extends trillions upon trillions of miles into surrounding space, claiming a volume of cosmic territory so huge that the planets, all 8 of them, take up an almost invisible sliver at the very center. Now think about Voyager 1 again. Launched by NASA on September 5, 1977 on a Titan IIIe Centaur rocket, Voyager 1 is the farthest human-made object from Earth. After nearly 5 decades of continuous travel at about 38,000 miles per hour, it has covered roughly 15 billion miles from the Sun. 15 billion miles in 47 years. That sounds like an amazing achievement of human engineering. In many ways it is. Voyager 1 has crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, becoming the first human-made object to enter interstellar space. But here is the reality that takes away any sense of triumph. Despite traveling for nearly half a century at 38,000 miles per hour, Voyager 1 is still well inside the Sun extended gravitational sphere. It has not escaped our star neighborhood. It has barely entered the front yard. At its current speed, Voyager 1 would need about 73,000 years to cover the distance to Proxima Centauri, the nearest star to our Sun, if it were going that way, which it is not. 73,000 years. That is about 9 times longer than all of recorded human civilization. The fastest object our species has ever launched into space cannot reach the next star over in any time period that matters to the survival of nations, languages, or even species. This is the emptiness that defines our solar system. Not the planets, not the moons, not the rocky debris in the asteroid belt, or the icy fragments in the Kuiper belt. The defining physical feature of our solar system is the absolutely staggering volume of empty space between objects. Space that contains almost nothing. No air, no sound, no resistance, no landmarks, no rest stops. Just vacuum, going in every direction, for billions upon billions of miles, broken only by occasional lumps of rock, gas, or ice, so small compared to the distances between them that finding them requires exact mathematical coordinates rather than any kind of visual search. Let us make this feel real with a scale model. Imagine shrinking the sun down to the size of a large grapefruit, about 8 inches across. At that scale, Earth becomes a small pebble, less than an inch wide, sitting about 75 feet away from the grapefruit. Mars is a slightly smaller pebble at about 115 feet. Jupiter, the giant of our planetary family, becomes a ball about 6 inches in diameter, hovering at about 390 feet from the grapefruit. Saturn sits at about 717 feet. And Neptune, the farthest major planet, becomes a ball slightly smaller than Jupiter, sitting nearly half a mile away from that front door. Half a mile. And the sun in this model is something you could hold in one hand. The whole solar system, squeezed down to this human-friendly scale, would fit inside a modest, small town. And nearly every square foot of that town would be completely empty. No buildings, no trees, no objects of any kind. Just bare ground between a front door and a handful of scattered balls stretching toward the horizon. But it is the next step in this model that shows the true nature of the emptiness. At the same scale where the sun is a grapefruit and Earth is a pebble 75 feet away, the nearest neighboring star system, Proxima Centauri, would be about 4,000 miles away. Imagine standing at your front door in New York City. Proxima Centauri would be another front door sitting somewhere in the middle of the Pacific Ocean, halfway to Japan. 4,000 miles of empty, featureless land between one star and its nearest neighbor. That is the gap between suns in our part of the galaxy. The space between stars is not just bigger than the space between planets. It belongs to an entirely different kind of distance. It dwarfs everything inside the solar system by factors so extreme that direct comparison stops meaning much. Like comparing the width of a human hair to the distance across the Atlantic Ocean. And that space is not just empty. It is hostile in ways that go beyond simple vacuum. The interstellar medium, the material that fills the space between stars in our part of the Milky Way, contains on average about 1 atom per cubic centimeter. That is incredibly sparse compared to any environment on Earth. The air in your living room has about 25 billion molecules per cubic centimeter. But even at this extremely low density, the interstellar medium is not nothing. It has stray hydrogen atoms, helium atoms, tiny amounts of heavier elements, microscopic dust grains, and a bath of high-energy cosmic ray particles, sped up to nearly light speed by distant supernovas and other violent astrophysical events. Magnetic fields run through this medium, weak but measurable, stretching across light years of space. For a spacecraft moving at low speeds like Voyager 1, this material does not matter. The density is far too low to cause any measurable drag or damage. But for a spacecraft moving at any significant fraction of the speed of light, the interstellar medium turns from an invisible background into a serious physical danger. At 10% of light speed, about 67 million miles per hour, each individual hydrogen atom that hits the spacecraft would strike the hull with the energy of a high-energy particle accelerator collision. Over a 4-light-year trip to Proxima Centauri, the constant bombardment from trillions upon trillions of these impacts would deliver a heavy dose of radiation to the spacecraft's surface, wear down shielding materials, and could damage sensitive instruments beyond repair. The interstellar medium also has dust grains, each one microscopic by Earth standards, but moving at 10% of light speed, each grain impact would carry the kinetic energy of a small, explosive charge. The void between stars is not a passive emptiness waiting to be crossed. It is a thin, invisible gauntlet that gets more dangerous the faster you try to cross it. Even at the smallest interstellar scales, even inside the relatively dense disk of our own galaxy, the space between stars punishes speed and rewards a kind of patience that no living organism has. And yet these interstellar gaps are just the spaces between individual houses in a city of 400 billion houses. All of this, the planets, the sun, the Voyager spacecraft, the 15 billion miles of distance traveled over nearly 5 decades, exists inside a single galaxy, the Milky Way. A structure so vast that the whole solar system, with all its planets and moons and comets and billions of miles of empty space, would not show up as a single visible dot on a photo taken from outside it. The numbers that describe the Milky Way are so far beyond anything we have seen so far that they need their own full treatment. But first, understand this. Everything measured so far, every distance that made your intuition flinch, every comparison that forced you to rethink what counts as large, describes a region of space so tiny inside our galaxy that it is, for all practical purposes, invisible. Here is where everything we have measured collapses into meaninglessness. If you placed a single grain of rice at the 50-yard line of an American football field and said that grain was the whole solar system, the football field would not even begin to represent the Milky Way. At that scale, our galaxy would stretch far past the stadium, past the parking lot, past the surrounding neighborhoods, past the city limits. The grain of rice sitting at midfield would be invisible to anyone in the stands. You could walk down to the 50-yard line, get on your knees, and search the grass with a magnifying glass, and you would struggle to find the grain that stands for everything you have ever known. Every signal humanity has ever sent into space has traveled outward at the speed of light for about 120 years, since the first radio broadcasts in the early 20th century. That means our electromagnetic footprint, the total of every radio wave, every television signal, every radar pulse, every intentional and unintentional transmission our species has ever produced, reaches about 120 light years from Earth in all directions. 120 light years sounds huge, but the Milky Way is 100,000 light years across. Our loudest shout into the cosmos has covered about 1/10% of our own galaxy diameter. If the Milky Way were a dining room table, our whole radiosphere would be a penny lying on the surface. To any observer on the other side of the galaxy, to any civilization watching from 50,000 light years away, humanity does not exist. Our signals have not arrived. They will not arrive for tens of thousands of years. And even when they do, they will be so faint, so spread out by the inverse square law that governs electromagnetic radiation, that detecting them would require sensitivity far beyond anything we can currently build. This is not guesswork. These are distances measured by space telescopes, confirmed by multiple independent research teams, published in peer-reviewed astrophysics journals, and verified across decades of observation. The European Space Agency Gaia spacecraft has cataloged the exact positions and motions of nearly 2 billion individual stars in our galaxy. NASA Hubble and James Webb Space Telescopes have imaged structures at distances that make the whole Milky Way look like a single spark in a bonfire. The measurements are confirmed, the numbers are real, and they are only the starting point of this story. Because everything described so far, every measurement, every distance, every comparison that stretched or broke your intuition, describes only our solar system and its position inside the galaxy it lives in. We have not yet looked beyond the Milky Way. We have not yet seen what lives just outside our galactic borders. A structure so large it makes our whole galaxy look modest by comparison. A structure with about 1 trillion stars spread across a disk more than double the diameter of our own. A structure that is right now, at this very moment, closing the distance between itself and us. The giant next door has a name, and by every measurable standard available to modern astronomy, it is bigger than the place we call home. So far we have measured Earth, we have measured the Sun, we have measured the distances between planets and the emptiness that fills our solar system. Every single one of those measurements felt huge at human scale, and every single one of them collapsed into insignificance the moment we placed it inside the context of the Milky Way galaxy. The solar system, with all its planets and moons and comets and billions of miles of empty space, became an invisible speck inside a structure with hundreds of billions of stars spread across 100,000 light-years of space. That is where we stand, at the edge of local understanding, staring into a galaxy so large that our whole stellar neighborhood vanishes inside it, like a single grain of sand dropped into the ocean. Now we need to go further, because the Milky Way, as impossibly vast as it is, does not exist alone. And what sits next to it makes our galaxy look modest. But before we leave the Milky Way, we need to understand exactly what kind of structure we live in. Because only by grasping the full scale of our home galaxy can you appreciate how dramatically the next object dwarfs it. The Milky Way is a barred spiral galaxy. Seen from above, it would look like a huge pinwheel with curved arms of stars, gas, and dust spiraling outward from a dense central bar of older reddish stars. The disk of visible stars is about 100,000 light-years across. To cross it at the speed of light, the fastest anything can travel in this universe would take 100,000 years. A beam of light leaving one edge of the Milky Way on the day you were born would not reach the opposite edge until about 100,000 years after every trace of human civilization had turned to dust and been forgotten. That is the width of the galaxy we live in. 100,000 light-years of stars, gas, dust, dark matter, stellar nurseries, supernova remnants, neutron stars, black holes, and vast stretches of interstellar vacuum, all held together by gravity into a single rotating structure. The disk is relatively thin compared to its width. At about 2,000 light-years thick in the region near our sun, the Milky Way is shaped more like a dinner plate than a ball. But even 2,000 light-years of thickness is an enormous vertical span. Light takes 2,000 years to go from the top of the galactic disk to the bottom in our neighborhood. When the Romans were building their first roads across Europe, a photon leaving the upper surface of the Milky Way disk near our position would only now be arriving at the lower surface. 2,000 years of travel at the fastest speed the universe allows, just across the thin edge of the galaxy. Inside this disk, the Milky Way has between 200 billion and 400 billion individual stars. The exact number is not certain because our position inside the galaxy limits our ability to count stars on the far side, where thick clouds of interstellar dust block visible light. Infrared surveys have improved our estimates a lot, but a precise count of every star in the Milky Way is still beyond what we can do. What we do know is that the number is stunning. If you tried to count every star in our galaxy at a rate of 1 star per second, never stopping to eat, sleep, or rest, the job would take you somewhere between 6,300 and 12,700 years. You would have to start counting before the Egyptian pyramids were built and keep going without stopping past today and far into the future before you finished. Each of those hundreds of billions of stars is a sun. Some are much larger and brighter than ours. Blue supergiants shine with brightness over 100,000 times the sun output. Red hypergiants have diameters so huge that if you put one at the center of our solar system, its surface would reach past the orbit of Jupiter. Others are much smaller and dimmer. Red dwarf stars, which make up about 70% of all stars in the Milky Way, shine so faintly that not a single one is visible to the naked eye from Earth. Even though they are the most common type of star in the galaxy, our sun is somewhere in the middle of this stellar range. It is brighter than most stars, dimmer than many, larger than some, smaller than others. In a galaxy of hundreds of billions, our star is completely average. Our solar system is about 26,000 light-years from the galactic center. We are not near the core. We are not at the edge. We are about halfway out along the disk, inside a minor structure called the Orion Spur, which branches off between two of the galaxy's major spiral arms, the Sagittarius arm and the Perseus arm. In galactic terms, we live in the suburbs, not the dense, active downtown core where stars are packed thousands of times tighter than in our neighborhood, but not the empty outer rim where star density drops to almost nothing. We are in a middle region of a middle arm of a galaxy that, as we are about to see, turns out to be middle-sized among its immediate neighbors. The sun and everything bound to it by gravity orbits the galactic center at about 515,000 miles per hour. Even at this huge speed, the sheer size of the Milky Way means that one full orbit takes about 230 million years. This period is sometimes called a galactic year, and it gives one of the most disorienting shifts in perspective in all of astronomy. In the 4.5 billion years since the solar system formed, the sun has made only about 19 or 20 full orbits around the galaxy. The last time our star was in this exact position in the Milky Way, about 230 million years ago, Earth was in the early Triassic period. Dinosaurs were just starting to appear. The supercontinent Pangaea was still mostly together. There was no grass anywhere on the planet, no flowers, no birds. The world was filled with creatures that would be almost unrecognizable to modern eyes. That is how long one galactic orbit takes. And the sun has done it only about 20 times in its whole existence. To understand how invisible our solar system is inside this structure, try one more comparison. If you were standing at the center of the Milky Way and looked outward toward our sun, finding it would be like standing in the middle of a completely dark Manhattan at night and trying to pick out one specific firefly among 400 billion other fireflies scattered across the island. Every firefly is glowing. Every firefly is moving. And the one you are looking for is completely average in brightness, completely average in size, and located in a part of the island with no special features at all. You would never find it, not in one human lifetime, not in 1,000 human lifetimes. Our sun and everything around it is one faint point of light among hundreds of billions in a galaxy 100,000 light-years across. This is the full scale of the Milky Way. It is the structure that holds every star you have ever seen in the night sky, every constellation, every planet visible to the naked eye, every meteor shower, every aurora. All of it happens inside this single galaxy. When you look up on a dark night and see the pale, milky band of light stretching across the sky, you are seeing the combined glow of billions of distant stars in the galactic disk, too far away to see individually, blending into a luminous river of light. That river is your home. It is the largest thing most people will ever think about, and it is not the largest thing in our immediate cosmic neighborhood. Not even close. On a clear autumn night in the northern hemisphere, if you know where to look, you can find a faint smudge of light in the constellation Andromeda. It looks dim, slightly fuzzy, easy to mistake for a small cloud or a flaw in your vision. Ancient astronomers listed it as a nebula, a cloud of glowing gas inside our own galaxy. For centuries, that is what scientists thought it was. The idea that this smudge could be anything bigger than a local gas cloud did not seriously enter scientific discussion until the early 20th century. And when the truth finally came out, it broke every existing model of how big the universe is. The story of that discovery deserves to be told properly, because it is one of the most dramatic single moments in the history of human knowledge. In the early 1920s, the scientific community was stuck in what became known as the Great Debate. On one side were astronomers who believed the Milky Way was the whole universe, with the spiral nebulae seen in telescopes being just clouds of gas inside our galaxy. On the other side were those who thought the spiral nebulae were island universes, whole galaxies like our own, located at huge distances beyond the Milky Way borders. Neither side had definite proof. The debate went on in lecture halls and journals, unresolved and increasingly bitter. Edwin Hubble settled it. He worked with the 100-inch Hooker telescope at Mount Wilson Observatory in Southern California, at that time the largest operating telescope on Earth. Hubble spent months taking long exposures of the Andromeda Nebula. The Hooker telescope unmatched light-gathering power let him see individual stars inside the nebula for the first time. He separated what had looked like a fuzzy glow into distinct points of light. Among these resolved stars, Hubble found a Cepheid variable, a type of star whose brightness pulses in a regular, predictable cycle. The key insight came from the work of astronomer Henrietta Swan Leavitt, who had shown years earlier through careful observations of Cepheids in the Magellanic Clouds that the pulsation period of a Cepheid is directly and reliably linked to its true brightness. A Cepheid that pulses slowly is genuinely brighter than one that pulses quickly. This period-luminosity relationship gave astronomers an incredibly powerful cosmic measuring tool. By watching the pulsation period of a Cepheid, you could figure out its true brightness. By comparing that true brightness to how faint it looked from Earth, you could calculate its distance using the inverse square law of light. Hubble applied this method to the Cepheid he found in Andromeda. The pulsation period told him the star's true brightness. How faint it looked from Earth told him it was enormously far away. When he finished the calculation, the result was staggering. The star, and therefore the nebula containing it, was about 900,000 light-years from Earth, a number later revised upward to about 2.5 million light-years as distance measurement methods improved. This was far beyond the estimated size of the Milky Way. The Andromeda Nebula was not a gas cloud inside our galaxy. It was a galaxy on its own, a separate island of stars at an almost unimaginable distance. In one calculation based on a pulsing star on a photographic plate, the known universe grew from one galaxy to at least two. The great debate was over. The cosmos had just become vastly larger than almost anyone had dared to suggest. That faint smudge you can see with your own eyes is the Andromeda Galaxy, listed as Messier 31 or M31 in astronomical catalogs. It is the most distant thing visible without a telescope. And what you are looking at, that gentle, barely noticeable glow, is the combined light of about 1 trillion stars. 1 trillion, not billion, trillion. To put that number in direct comparison, the Milky Way has between 200 billion and 400 billion stars. Andromeda has about 1 trillion. Depending on which estimate you use for our galaxy, Andromeda has between 2.5 to 5 times as many stars as the Milky Way. Every star in our galaxy, every sun that powers every planet that might hold life inside the Milky Way, could be multiplied several times over and still not match the star count of the galaxy next door. When you look at that faint smudge in the autumn sky, you are seeing a structure with more individual suns than the total number of stars in your home galaxy. That simple act of looking, something any person with normal eyesight can do on a clear night, connects your retina to photons that started from a system of 1 trillion nuclear furnaces burning across a disk of space more than twice as wide as everything you have ever known. Andromeda disk is about 220,000 light-years across. The Milky Way disk is about 100,000 light-years across. Put the two galaxies side by side, and Andromeda would dwarf our galaxy the way a beach ball dwarfs a tennis ball. More than double the diameter means far more than double the area. The surface area of Andromeda disk is about 4 to 5 times that of the Milky Way disk. It is not just a bigger version of our galaxy. It is a completely different level of structure, a galactic giant that makes our home look like a smaller companion rather than an equal neighbor. The structural differences go beyond just size. Andromeda is also a spiral galaxy, but its spiral arms are wound tighter than the Milky Way arms. And its central bulge, the dense crowd of older stars around the galactic core, is much more prominent. The Milky Way central bulge is fairly modest and stretched into a bar shape. Andromeda bulge is rounder and more massive, with a much larger population of older, redder stars. This structural difference tells astronomers something important about each galaxy history. The size and shape of a central bulge is shaped by a galaxy merger history. Larger bulges usually mean more past crashes with other galaxies. Andromeda Big Bulge suggests it has eaten more satellite galaxies over its lifetime than the Milky Way has, growing its central regions through repeated gravitational cannibalism over billions of years. Both galaxies have supermassive black holes at their centers. In the Milky Way, the central black hole is called Sagittarius A star. It weighs about 4 million times the mass of our Sun. 4 million solar masses sounds huge, and it is. But Andromeda's central black hole is much bigger. Called M31 star, it weighs about 100 million solar masses. That is about 25 times heavier than the Milky Way central black hole. If Sagittarius A star is a boulder at the center of our galaxy, Andromeda black hole is a small mountain. This difference in central black hole mass also reflects the difference in each galaxy accretion history. Larger black holes grow by eating more material over cosmic time, fed by falling gas and by mergers with other black holes brought in by swallowed satellite galaxies. Andromeda, a much larger central black hole, tells us that it has had access to and consumed far more material than our galaxy core. The globular cluster populations of each galaxy give another point of comparison. Globular clusters are ancient, dense, round collections of stars that orbit a galaxy core. They are among the oldest structures in any galaxy, with many dating back to within 1 billion years of the Big Bang. The Milky Way has about 150 known globular clusters. Andromeda has about 450, about 3 times as many. Some estimates put Andromeda globular cluster count even higher, toward 500 or more. Each globular cluster holds anywhere from tens of thousands to several million stars, packed into a spherical volume only a few dozen to a few hundred light-years across. The sheer number of globular clusters orbiting Andromeda shows the galaxy's larger gravitational influence and its more extensive history of swallowing satellite galaxies. But Andromeda dominance goes beyond its internal structure. It commands a whole gravitational entourage of smaller galaxies. The two most prominent satellite galaxies are M32 and M110. Both can be seen in long-exposure photos of Andromeda as distinct, smaller smudges near the main disk. M32 is a compact elliptical galaxy with about 3 billion stars. Even though it is fairly small, M32 is scientifically interesting because it orbits very close to Andromeda disk and shows clear signs of tidal stripping. Andromeda's huge gravity is actively pulling stars away from M32 outer regions, slowly taking it apart over hundreds of millions of years. Computer models suggest that M32 may once have been a much larger galaxy, maybe a medium-sized spiral that has been gradually eaten by Andromeda over billions of years of close orbital interaction, stripped down to its dense core. M110, a dwarf elliptical galaxy, orbits at a somewhat larger distance, but also shows evidence of gravitational disturbance from its massive host. Its outer parts look diffuse and irregular, matching what you would expect from tidal interactions stretching its structure. Beyond these two well-known companions, Andromeda has at least 35 confirmed satellite galaxies, and probably more waiting to be found in deeper surveys. This group of satellites mirrors the Milky Way's own collection of dwarf companions, including the large and small Magellanic Clouds visible from the southern hemisphere. But Andromeda's satellite system is both more numerous and includes objects in more advanced stages of tidal disruption. Andromeda is not just a bigger galaxy. It is a more active gravitational predator, eating its smaller neighbors more aggressively than the Milky Way currently eats its own. The evidence of this ongoing cannibalism is written across the streams of tidally stripped stars and disturbed satellite orbits that surround Andromeda disk. The total mass of each galaxy gives perhaps the most scientifically meaningful comparison, though it is also the most complicated. Galaxy mass includes not just stars and gas, but the huge invisible halos of dark matter that surround every large galaxy. These dark matter halos reach far beyond the visible disk of stars, sometimes out to several 100,000 light-years from the galactic center. Dark matter does not emit, absorb, or reflect light, so telescopes cannot see it. We know it is there only through its gravitational effects on visible matter, the rotation speeds of stars, the orbits of satellite galaxies, and the bending of light from background objects. Current estimates put the Milky Way total mass, including its dark matter halo, at about 1 to 1.5 trillion solar masses. Andromeda total mass has been the subject of a lot of scientific debate. Earlier estimates placed it significantly higher than the Milky Way mass, at about 1.5 to 2 trillion solar masses, supporting the picture of Andromeda as the dominant galaxy in our local area. However, more recent studies, especially those using data from the European Space Agency Gaia spacecraft, have revised some of these estimates. A 2018 study published in the Astrophysical journal used the movements of satellite galaxies and globular clusters orbiting Andromeda to recalculate its total mass and came up with a number closer to 800 billion solar masses, surprisingly lower than earlier estimates, and possibly about the same as or even a little less than the Milky Way mass. Other studies have given different results, with mass estimates for Andromeda ranging from 800 billion to nearly 2 trillion solar masses, depending on the method, assumptions about the dark matter halo shape, and which tracer objects are used to measure the gravitational field. What this means in practical terms is that while Andromeda is clearly larger in terms of stellar disk diameter, star count, central black hole mass, and globular cluster population, the question of which galaxy is more massive overall is still an open area of research. The Milky Way may be the less visually impressive galaxy, but it is not necessarily the less massive one. The two galaxies may be closer to equal in total mass than decades of popular astronomy have suggested. This uncertainty itself is scientifically fascinating. It tells us that measuring the total mass of a galaxy, especially the invisible dark matter component that makes up most of the mass, is still one of the hardest problems in modern astrophysics. Even for our nearest giant galactic neighbor, a galaxy close enough to see without a telescope, we cannot yet agree on how much it weighs. But no matter where the total mass comparison finally ends up, the visible differences are dramatic and impossible to ignore. Andromeda disk is more than twice the diameter of ours. Its star count is 2 to 5 times higher. Its central black hole is 25 times heavier. Its globular cluster system is 3 times richer. In every way you can see, Andromeda is the larger galaxy. If the Milky Way is a medium-sized city, Andromeda is a sprawling metropolis. Both are impressive. Both are huge. But one of them has more buildings, wider streets, a denser downtown, and a much bigger city hall. And both of them belong to the same gravitational neighborhood. The Milky Way and Andromeda are the 2 largest members of a collection of galaxies called the Local Group. This gravitational family has more than 80 individual galaxies, though most of them are small dwarf galaxies with only a few billion stars or fewer. The Local Group spans about 10 million light-years across, with the Milky Way and Andromeda acting as the 2 main gravitational anchors around which everything else orbits. The 3rd largest member, the Triangulum Galaxy, has about 40 billion stars and sits about 3 million light-years from us, fairly close to Andromeda and possibly bound to it as a satellite. The Local Group is not a dense cluster. It is a loose association of galaxies held together by mutual gravity, with most of its volume being empty intergalactic space. The smaller dwarf galaxies orbit either the Milky Way or Andromeda, much like moons orbit planets. The Milky Way has about 50 known satellite galaxies. Andromeda has a similar or slightly larger number of satellite dwarfs. These smaller galaxies are slowly being pulled inward by their host galaxy gravity, and many of them will eventually be torn apart and absorbed, their stars scattered into the halo of whichever giant galaxy takes them. The Milky Way and Andromeda dominate everything. Together they hold the vast majority of the group total mass and stellar population. They are the gravitational kings of this particular cosmic neighborhood. And every smaller galaxy within 10 million light-years exists under their combined influence. But these 2 kings are not sitting still. They're not keeping a polite distance from each other in a quiet cosmic suburb. The Milky Way and Andromeda are separated by about 2.5 million light-years of intergalactic space. That distance is enormous by any human measure. It is a gulf so wide that light itself, moving at 186,000 miles per second, takes 2.5 million years to cross it. The photons reaching your eyes from Andromeda tonight left that galaxy before the genus Homo existed on Earth. And across that whole vast distance, something is happening. Something slow, gravitational, and unavoidable. Andromeda is not drifting randomly through space relative to us. It is not moving away like most distant galaxies carried apart by the expansion of the universe. Andromeda is approaching. The blue shift of its light, first measured in the early 20th century and confirmed with better and better precision ever since, tells us that the space between our galaxy and Andromeda is shrinking. The gap is closing at about 110 kilometers per second, roughly 250,000 miles per hour. 2 galaxies, each with hundreds of billions to a trillion stars, separated by 2.5 million light-years of nearly empty space, are moving toward each other because of mutual gravitational attraction. 2.5 million light-years. That is the distance between the Milky Way and the Andromeda Galaxy. It is the number that has been in the background of this whole story, waiting for the moment when we finally stop and look straight at it. We have spent this entire journey building up to this distance. We measured Earth and found it huge at human scale, but invisible at planetary scale. We measured the solar system and found it vast by any earthly standard, but invisible inside the Milky Way. We measured the Milky Way and found it impossibly large, with hundreds of billions of stars across 100,000 light-years of space. And then we discovered that the galaxy next door, Andromeda, is more than twice the diameter of our home, holds up to 1 trillion stars, and has a central black hole 25 times more massive than ours. Each step of this journey has destroyed the sense of scale from the step before. Each level of cosmic organization has made the last one disappear. Now we face the gap between them. And this is where the numbers stop acting like numbers. This is where the human brain, which evolved to track the distance between a predator and a water hole, hits a wall it cannot climb. 1 light year is the distance light travels in 1 year, moving at about 186,000 miles per second. In more familiar terms, 1 light year is about 5.88 trillion miles. That is 5,880 billion miles. Written out fully, that number is 5 followed by 12 zeros. A single light year is already so far beyond anything a human has ever traveled that it works more as a math concept than a real distance. No human has gone even 1% of 1 light year from Earth. The farthest any person has ever been from this planet is the distance to the moon, about 240,000 miles during the Apollo missions. 1 light year is about 24 million times farther than the moon. Every crewed space mission in human history, every walk on the moon, every orbit of Earth, every spacewalk from the International Space Station, all of it combined does not come close to 1 light year of travel. Now multiply that number by 2.5 million. The distance to the Andromeda Galaxy is about 2.5 million light years, which is about 14.7 quadrillion miles. 14.7 quadrillion. That is 14,700,000 billion miles. The number has 15 digits. It is so large that writing it out in standard form makes you count zeros the way you might count steps on a long staircase, losing track somewhere in the middle and having to start over. 14.7 quadrillion miles is not a distance you can understand. It is a distance you can only accept as a proven fact, while admitting that your nervous system has no way to turn it into a picture, a feeling, or an intuition. But let us try anyway. Let us try to turn this distance into something physical. Light moves at the fastest speed the universe allows. Nothing with mass can match it. Nothing with mass can even get close without needing an infinite amount of energy. And yet light moving at this ultimate cosmic speed takes 2.5 million years to cross from Andromeda to the Milky Way. Think about what that travel time contains. 2.5 million years ago, the genus Homo did not exist. Our ancestors were Auroran, walking upright across the African savanna with brains about 1/3 the size of a modern human. They had no language, no tools beyond maybe an occasional rock they found, no fire, no shelter beyond what the landscape gave them. They lived and died within walking distance of where they were born, knowing nothing beyond the immediate horizon. The light reaching your eyes from Andromeda tonight left that galaxy before any of that. It left before the evolutionary branching that would eventually produce Homo habilis, the first species in our line to make stone tools on purpose. It left before Homo erectus learned to control fire, before Homo sapiens developed language, before farming, before cities, before writing, before math, before telescopes, before the idea of a galaxy even entered human thought. The whole arc of human evolution, every biological and cultural step that separates you from a small-brained primate on the African plains, fits inside the travel time of 1 beam of light crossing from Andromeda to here. That light was already ancient when the first humans looked up at the night sky and wondered what the stars were. It was already ancient when Galileo pointed his telescope at Jupiter. It was already ancient when Edwin Hubble proved that the smudge in Andromeda was not a nebula inside our galaxy, but a separate galaxy entirely. 2.5 million years of travel at the speed of light, and light is the fastest thing there is. Now consider what fills that distance, or more precisely, consider what does not fill it. The intergalactic space between the Milky Way and Andromeda is not perfectly empty. Scientists have found extremely thin distributions of matter in this region. Hot ionized gas, mostly hydrogen and helium, exists in intergalactic space at temperatures of hundreds of thousands of degrees. Thin threads of dark matter run through the void, leftovers of the large-scale cosmic web that connects galaxies across the universe. Once in a while, a lost star thrown out from one galaxy or the other drifts through this space, not bound to any galaxy, moving alone through the dark at hundreds of thousands of miles per hour with no destination and no companions. But the density of this material is so incredibly low that calling it matter is almost too generous. The average density of intergalactic space in the region between the Milky Way and Andromeda is about 1 atom per cubic meter. 1 atom. In a space the size of a large cardboard box, you would find on average 1 hydrogen atom. For comparison, the air you are breathing right now has about 25 quintillion molecules per cubic centimeter. The difference in density between the air in your lungs and the intergalactic medium between here and Andromeda is a factor of about 10 to the 25th power. It is a difference so extreme that intergalactic space is the most perfect vacuum that naturally exists anywhere in the known universe. Laboratory vacuum chambers on Earth cannot match this level of emptiness. The best vacuum systems ever built by human engineers still have millions of molecules per cubic centimeter. Intergalactic space is emptier than anything we can make. Imagine a swimming pool filled with perfectly pure water. Then imagine removing every molecule from that pool except for 1 grain of dissolved salt. That pool would still have more matter per unit volume than the intergalactic void between our galaxy and Andromeda. This is the space that separates us from the nearest giant galaxy. 2.5 million light-years of almost perfect nothing. No waypoints, no landmarks, no large objects to navigate by, no sources of fuel or energy, no raw materials for building or repair, no electromagnetic signals strong enough to act as beacons, just a flat, featureless, almost empty gulf, stretching for 14.7 quadrillion miles in every direction, between 2 islands of organized matter that are, compared to the distance between them, vanishingly small. And across this void, Andromeda is moving toward the Milky Way. This is not a theory. It is proven by observation. The evidence comes from looking at Andromeda light through a spectroscope. When an object moves toward an observer, the wavelengths of light it gives off are squeezed, shifting toward the blue end of the spectrum. This is called blue shift. It is the approaching object version of a police siren rising in pitch as it drives toward you. Andromeda light is blue shifted. The galaxy is approaching. This was first measured by astronomer Vesto Slipher in 1912 at Lowell Observatory in Flagstaff, Arizona, making Andromeda one of the first galaxies ever found to have a significant speed relative to our own. The measurement has been confirmed and improved continuously in the century since. The current best estimate for Andromeda approach speed directly toward us is about 110 kilometers per second, which is about 250,000 miles per hour. At that speed, the gap between the 2 galaxies shrinks by about 110 kilometers every second. Over 1 Earth year, Andromeda moves about 3.5 billion kilometers closer to us, about 23 astronomical units, or about 23 times the distance from Earth to the Sun. Every year, a span equal to nearly the distance from the Sun to Uranus is erased from the intergalactic gap. That sounds fast, and on Earth, it is fast. 250,000 miles per hour is faster than any human-made object by a lot. It is fast enough to go from Earth to the Moon in about 1 hour. But compared to the scale of intergalactic space, it is extremely slow. At 110 kilometers per second, closing the full 2.5 million light-year distance to Andromeda would take about 4 to 5 billion years. That is about as long as Earth has already existed. The trip that Andromeda is making toward us has been going on for billions of years already, and will continue for billions more. You will never see it happen. Your civilization will never see it happen. The whole time humans exist on this planet, from the first Homo sapiens to whatever end we eventually meet, will not be long enough to notice any visible change in Andromeda position in the night sky without a telescope. Here's where the science gets more complicated than most popular stories admit. For decades, the standard description of the Milky Way Andromeda meeting has been simple. The 2 galaxies are on a crash course. They will hit head-on in about 4 to 4.5 billion years. The merger will make one big elliptical galaxy. This story has appeared in countless documentaries, textbooks, popular science articles, and planetarium shows. It is one of the best-known facts in public astronomy. But the full picture is more detailed, and what scientists understand has changed a lot in the last 10 years. The speed of Andromeda directly toward us is well measured, 110 kilometers per second, confirmed by many separate studies. However, that number only tells you how fast the gap is closing along the straight line between the 2 galaxies. It does not tell you how Andromeda is moving sideways relative to that line. This sideways part, called the transverse velocity, is critical for predicting whether the 2 galaxies will hit head-on, give each other a glancing blow, or even miss on the first pass and then be pulled back together by gravity for a later merger. Measuring the sideways speed of a galaxy 2.5 million light-years away is extremely hard. The sideways motion shows up as a tiny angle change in the sky, so small it is almost impossible to detect. For years, the transverse velocity of Andromeda was basically unknown, and most models just assumed it was small enough that a head-on crash was the most likely result. This changed with the European Space Agency Gaia spacecraft. Gaia was built to measure the exact positions and movements of stars with incredible accuracy. By tracking the average motion of stars inside Andromeda compared to background quasars, researchers were able to make the first solid measurements of Andromeda transverse speed. Studies published in 2019 using Gaia data release 2 put Andromeda sideways speed at about 57 kilometers per second, with uncertainty allowing values from about 40 to 70 kilometers per second. This is not small. A significant sideways component means the two galaxies are not coming straight at each other. They are on a path that includes a large sideways offset. What does this mean for the future meeting? Several things, all of which add real uncertainty to the story. A higher sideways speed makes a direct head-on crash on the first pass less likely, and a glancing encounter more likely. Instead of one dramatic impact, the galaxies might do an initial flyby, coming close enough for their dark matter halos and outer stars to feel each other gravity, but without the immediate full merger that older models predicted. After the first pass, gravitational friction and the ongoing pull between the two galaxies would gradually slow their relative motion, pull them back together, and set up a second approach. This second encounter would probably be closer and slower, leading to a more complete gravitational mixing. More passes would follow, each one bringing the galaxies closer and wasting more orbital energy, until eventually, over a period that might be several billion years after the first close approach, the two systems would blend into one structure. This updated picture pushes the timeline for a full merger farther into the future. From the commonly quoted 4 to 4.5 billion years to maybe 5 billion, 6 billion, or even closer to 10 billion years, depending on the exact orbital details. Some models suggest the first close pass could happen in about 4.5 billion years, but the final merger might not be done until 8 to 10 billion years from now. It is important to say clearly what scientists agree on and what they are still debating. Everyone agrees that the Milky Way and Andromeda are gravitationally bound to each other and are moving toward each other. The radial blue shift is confirmed. The gravity pulling them together is real. Some kind of major interaction will happen. What is still being figured out is the exact geometry of the meeting, whether the first pass is a head-on hit or a glancing flyby. The exact timeline for first close approach, how many orbits or passes happen before full merging, and the final shape of the combined galaxy. These details depend on measurements that are still being improved, especially the transverse speed, the total masses of both galaxies, including their dark matter halos, and the dynamical friction effects that will control how fast orbital energy is lost. The honest scientific answer is this: a crash is very likely. A merger is almost certain over a long enough time. But the exact dance of 2 trillion star systems moving toward each other across 2.5 million light-years is still being worked out. Anyone who says they know exactly when and how it will happen is leaving out the complexity. Now, set aside the debate about timing and geometry and ask a more basic question. What does a galactic merger actually look like? Popular imagination brings up images of huge explosions, fireballs, stars crashing, planets blowing up. That picture is almost completely wrong. A galaxy merger is not a crash in any way that a human would recognize. Stars do not hit each other. The reason is simple and has everything to do with the emptiness we talked about earlier. Stars inside galaxies are separated by truly enormous distances compared to how big they are. In our solar neighborhood, the average gap between neighboring stars is about 4 to 5 light years. Each star is a few 100,000 to a few million miles across, but the spaces between them are trillions of miles. If you shrank the sun to the size of a bowling ball and put it in the center of a large cathedral, the nearest bowling ball representing the nearest star would be in a completely different cathedral, in a different city hundreds of miles away. The space between stars is so large compared to the stars themselves that during a galaxy merger, the chance of any two stars physically hitting each other is incredibly small. Statistically, it is almost zero. You could run the whole merger simulation billions of times, and direct star collisions would still be extremely rare. What does happen, though, is dramatic in a gravitational sense. When two galaxies pass near or through each other, the gravitational forces involved are huge and work across scales of thousands of light years. These tidal forces do not need to smash stars together to reshape both galaxies completely. They warp orbits, they stretch spiral arms, they throw stars onto entirely new paths, sending some on long, looping trips into intergalactic space and pulling others deep into the merged galactic core. The neat, beautiful spiral patterns that mark both the Milky Way and Andromeda would be slowly twisted, stretched, and eventually destroyed. Over hundreds of millions of years after the first close pass, the spiral arms would break apart into chaotic streams and shells of stars. The orderly disk shapes would puff up into a rounder, less organized form. Meanwhile, the gas inside both galaxies would act very differently from the stars. Stars, being compact and widely spaced, pass through each other galaxy space without touching. Gas clouds, however, are spread out and fuzzy. When the gas from two galaxies meets during a merger, it crashes together, compresses, and gets hot. This compression sets off huge waves of new star formation. Parts of both galaxies that had been quiet for billions of years would suddenly light up with the birth of millions of new stars, glowing in infrared and ultraviolet. Astronomers see this happening right now in other merging galaxy pairs across the universe. Systems like the Antennae galaxies, two spirals currently colliding about 63 million light-years from Earth, show amazing bursts of star formation in the regions where they overlap, just as models predict. The antennae are not unique. NGC 4676, often called the mice galaxies, shows two spirals caught in an earlier stage of gravitational interaction. Their long, tidal tails stream outward like trails of debris from a slow-motion accident, stretching hundreds of thousands of light-years into intergalactic space. The Cartwheel galaxy, about 500 million light-years away, shows an even rarer and more violent shape. It is a ring galaxy, formed when a smaller galaxy punched straight through the center of a larger spiral disk at high speed, sending a shockwave of compressed gas and triggered star formation, radiating outward in an expanding ring, like a ripple spreading across the surface of a cosmic pond. The smaller galaxy went all the way through and is still visible nearby, leaving behind a bullseye pattern of new stars unlike anything in our local cosmic area. These systems are not simulations or guesses. They are real galaxies seen at different stages of gravitational interaction, giving us a visual catalog of what the Milky Way Andromeda meeting will look like across different phases, separated by hundreds of millions of years. Astronomers study these systems as stand-ins for our own galaxy future, using what they see to check and improve computer models of the eventual Milky Way Andromeda merger. This starburst phase would be temporary. The violent gas compression uses up the available fuel fairly quickly in cosmic terms. Within a few hundred million years, the easily accessible gas would either be turned into new stars, heated too much to collapse, or blown out of the merger area entirely by the energy from the newly formed stars and any active galaxy cores triggered by gas falling toward the central black holes. After the starburst, star formation would drop sharply and the merged galaxy would start to calm down. The end state, reached maybe 1 to 2 billion years after the final blending, would be a massive elliptical galaxy. No spiral arms, no disk, just a roughly round or slightly stretched blob of stars orbiting a common center of mass in random directions. Astronomers have suggested several names for this future merged galaxy: Milka, Milkdromeda. The names are playful, but the structure they describe would be huge. A combined system with somewhere between 1.5 and 2 trillion stars, with a total mass possibly above 2 trillion solar masses, ruled by 1 or 2 supermassive black holes at its center, that would themselves eventually merge in a huge event, sending out gravitational waves detectable in principle across the observable universe. What about our solar system? If the sun still exists when the merger happens, which depends on the timeline, it would be near the end of its normal life in about 5 billion years. The full merger might not be done until several billion years after that. But if we assume the sun, or what is left of it, survives at least the early stages of the interaction, The most likely result is not destruction, but moving. The sun would probably not hit any other star, for the same reason that star collisions are extremely rare across the whole merger. However, gravitational disturbances could change the sun orbit a lot. It might be thrown outward into the halo of the merged galaxy, orbiting much farther from the center than it does now. It might be pulled inward toward the galactic core. In some simulations, a small number of stars are thrown completely out of the merged system, flung into intergalactic space at high speed, becoming lost rogue stars drifting through the void with no galaxy to call home. From the point of view of anyone living on a planet around a star caught in this merger, the changes would be too slow to notice on human timescales. Galaxy mergers take hundreds of millions of years. The night sky would change slowly over thousands and millions of years. Unfamiliar stars from Andromeda would appear in constellations that slowly twisted beyond recognition. The band of the Milky Way across the sky would warp, brighter in some areas, dimmer in others, and eventually dissolve into a more even glow. As the disk structure was destroyed, new nebulae would appear where star formation burst out in compressed gas clouds. But none of this would happen fast enough for any one person or even any civilization lasting thousands of years to see a sudden change. A galaxy merger is an event measured in geological time, not human time. It would be like watching a mountain wear away. The process is real, powerful, and world-changing, but you would never see it move. This is the reality of the Milky Way-Andromeda interaction. Two structures, each with hundreds of billions to a trillion stars, moving toward each other across 2.5 million light-years of nearly perfect vacuum at 250,000 miles per hour. The meeting will take billions of years to play out. The merger will change both galaxies beyond recognition. Stars will be scattered, orbits rewritten, spiral structures erased. A new, larger galaxy will come out of the gravitational wreckage of two ancient spirals. And not one star in either galaxy is likely to physically touch another star during the whole process. The distances are too large. The stars are too small. The timescales are too long. That combination, the interplay of huge distances, tiny objects, and billion-year timescales, defines not just this merger, but the basic character of the universe at the galaxy level. Which brings us to the question that this whole story has been building toward. Not what the universe will do on its own schedule. The universe has no interest in human schedules or human abilities. The universe runs on timescales that make civilizations look like sparks from a campfire, bright for a moment and then gone. The question is what this scale means for anyone who lives inside it. What does 2.5 million light-years mean for a species that builds rockets? What does a trillion-star galaxy mean for a civilization that has not yet reached the nearest star to its own sun? What does intergalactic distance mean for any living thing, any technological society, any possible intelligence that looks up at Andromeda from a small planet in the Milky Way and wonders if it could ever go there? The distances we have measured in this story are not abstract. They are physical. They are made of real space. Crossing them takes real time, real energy, and real technology. The laws of physics that say how fast matter can move through space, how much energy it takes to speed up mass, and how long living things can survive are not suggestions. They are hard limits. And what comes next will measure those limits against the distance to Andromeda and find exactly where the line is between what human ambition can dream of and what the structure of the universe will actually allow. That line is closer than you think, and it is much more absolute than anything we have seen so far. We have now measured everything. We know the size of Earth. We know the size of the Sun. We know the distances between planets and the emptiness that fills our solar system. We know the scale of the Milky Way with its hundreds of billions of stars and the staggering size of the Andromeda Galaxy with its trillion suns stretching across 220,000 light-years of space. We know the distance between our galaxy and Andromeda, 2.5 million light-years, 14.7 quadrillion miles of nearly perfect vacuum. We know that Andromeda is approaching. We know a gravitational meeting is coming. We know the merger of these two galaxies will play out over timescales measured in billions of years. All of these are confirmed, measured, published, proven facts. The numbers are real. The distances are real. The physics is real. Now comes the part of this story that no amount of engineering optimism or technological dreaming can soften. Now we ask the question that every measurement in this journey has been quietly leading to. Could we ever cross that distance? Could any civilization using any technology, ruled by any biology, ever travel from the Milky Way to the Andromeda Galaxy within a time period that means anything to the beings who try? The answer is crushing. And it comes not from pessimism, but from simple math. Start with what we have actually built. The fastest object humanity has ever sent into deep space on a path away from the sun is Voyager 1, moving at about 38,000 miles per hour relative to the sun. At that speed, Voyager 1 covers about 333 million miles per year. That sounds fast. It is fast by any standard humans have ever used for travel. It is faster than any car, any airplane, any bullet, any rocket vehicle that has ever carried a person. And it is laughably, disastrously too slow for intergalactic distances. At 38,000 miles per hour, traveling non-stop without slowing down, without any interruption, without hitting any obstacle or gravitational interference, Voyager 1 would need about 44 billion years to reach the Andromeda Galaxy. 44 billion years. The current age of the universe from the Big Bang to this moment is about 13.8 billion years. The trip to Andromeda at Voyager speed would take more than 3 times the whole age of the universe. The universe itself has not existed long enough for our fastest spacecraft to finish this trip. If Voyager 1 had been launched at the moment of the Big Bang, traveling through the young cosmos before galaxies or stars or planets had even formed, it would still not have arrived at Andromeda by now. It would still have about 30 billion years of travel left. That is, the gap between human engineering and intergalactic distance. It is not a gap that can be closed with small improvements. It is a gap at a completely different level of size from anything our species has ever faced. What about the Parker Solar Probe? As of recent measurements, it holds the record for fastest human-made object relative to the sun, reaching speeds of about 430,000 miles per hour during its closest passes near the sun. That is more than 11 times faster than Voyager 1. It is a real jump in speed for human-built hardware. And at that speed, reaching Andromeda would still take about 3.9 billion years. 3.9 billion years. Earth is 4.5 billion years old. That means the fastest object humanity has ever built would need a travel time about as long as the whole current age of our planet to get to the galaxy next door. Complex multicellular life has existed on Earth for about 600 million years. The whole history of animals from the Cambrian explosion to right now fits inside a window of time that is only a fraction of what the Parker Solar Probe would need. Its speed, which would flatten any normal object on Earth on contact, which is faster than the escape speed of every planet in our solar system, which is the absolute peak of current human propulsion achievement, gets us almost nowhere. It cuts the travel time from absurd to slightly less absurd. The destination is still unreachable by any measure that matters. But these are existing technologies. What about theoretical ones? What about propulsion systems that do not exist yet but are based on real physics? What about the ideas discussed in research papers and engineering meetings? The designs that might someday push a spacecraft to a meaningful fraction of the speed of light? The Breakthrough Starshot project, announced in 2016, proposed using ground-based lasers to push tiny, lightweight probes to about 20% of the speed of light. At that speed, such a probe could reach the nearest star, Proxima Centauri, in about 20 years. It is an ambitious concept. Even if all the engineering problems are eventually solved, the technology would be meant for interstellar distances measured in single-digit light years, not intergalactic distances measured in millions. But let us be generous. Let us assume a civilization far more advanced than ours manages to build a crude spacecraft capable of steady travel at 10% of the speed of light. This is not a small assumption. 10% of light speed is about 67 million miles per hour, nearly 2,000 times faster than Voyager 1. Reaching this speed with a crewed vehicle would require energy outputs and propulsion efficiencies so far beyond current ability that no serious engineering path exists to create them. But assume it anyway. At 10% of light speed, the trip to Andromeda would take 25 million years. 25 million years. To put that in biological context, 25 million years ago on Earth, the ancestors of modern great apes had not yet split from the ancestors of modern Old World monkeys. The Himalayas were still being pushed upward by shifting tectonic plates. The whole evolutionary line that led to modern humans, from early primates to Homo sapiens, could fit inside this travel time with room left over. A spacecraft that left at 10% of light speed when the first apes were swinging through Oligocene forests would arrive at Andromeda about now. The passengers on that ship, if biological passengers were even possible for such a trip, would need to support not just themselves but a whole working society, a closed ecosystem, a stable technical infrastructure, and a clear mission purpose across a period longer than most mammal species survive on Earth. The average lifetime of a mammal species from first appearance to extinction is about 1 to 2 million years. The trip to Andromeda at 10% of light speed would outlast whole evolutionary lines by a factor of more than 10. Go faster. Assume 50% of light speed. That is about 335 million miles per hour. At 50% of light speed, the trip to Andromeda takes 5 million years. 5 million years ago, the first members of the genus Australopithecus were appearing in Africa. Everything that separates those small-brained, ape-like hominins from you, every tool, every word, every idea, every city, every war, every scientific discovery, happened in the time it would take a half-light-speed spacecraft to reach Andromeda. And that spacecraft would need to keep its passengers or their descendants or some form of ongoing working intelligence alive across that whole span. Push speed further. Assume 99% of light speed. At this speed, relativity effects become important. Einstein's special theory of relativity says that time passes more slowly for objects moving at speeds close to light speed. This is called time dilation. For travelers on a spacecraft moving at 99% of light speed, their experience of time would be squeezed. The universe outside the ship would age faster than the people inside. This effect is real. It has been proven with high-precision atomic clocks flown on fast planes and satellites. It is not science fiction. It is measured physics. At 99% of light speed, the travel time is measured from outside. The time that passes for observers back in the Milky Way would still be about 2.5 million years. The universe does not care how fast you go. 2.5 million light years of distance still needs a minimum of 2.5 million years for light or anything near light speed to cross, as measured from the stationary frame. But inside the ship, time dilation would squeeze the experience. For a ship that could keep a steady acceleration of 1 gravity, which would also give Earth-like artificial gravity for the passengers, the felt journey time to Andromeda would be only about 28 years of ship time. 28 years! That sounds almost doable. A crew could leave in young adulthood and arrive in late middle age. But this picture hides problems so severe that they make the idea impossible for any real consideration. First, keeping 1 gravity of steady acceleration for the whole 2.5 million light-year trip would need an amount of energy so huge that no known or even theorized fuel source could provide it. The energy needed to speed up a spacecraft of any real mass to 99% of light speed, keep that acceleration going, and then slow down at the destination is more than the total energy output of the Sun over large fractions of its lifetime. This is not a hard engineering problem. This is an energy requirement that would use up star-sized power sources. Second, the travelers who arrived at Andromeda after 28 felt years would step out of their ship into a universe that had aged by 2.5 million years. Everyone they knew, every civilization they left behind, every record of their leaving would be gone. Not dead for a few generations, gone for 2.5 million years. The Milky Way they left would not be recognizable. Stars would have been born and died. Star populations would have shifted. The very position of their home star inside the galaxy would have changed. They would arrive as visitors from a past so distant that nothing from their time would remain. Even if the physics of the trip were solved, the travelers would be permanently cut off from everything and everyone that existed when they left. This is not exile. It is erasure. And the erasure would go both ways. Not only would the Milky Way they left have aged beyond recognition, but the Andromeda they aimed for would no longer be in the form they studied before leaving. The galaxy whose maps they carried whose star charts they memorized, whose spiral arm shapes guided their approach path, would have gone through 2.5 million years of star changes during their trip. Huge blue stars that shone brightly in their pre-departure observations would have run out of fuel and exploded as supernovas, leaving behind neutron stars or black holes where bright landmarks once were. Millions of new stars would have formed in areas that were nothing but cold gas clouds when the mission was planned. The spiral arms would have rotated to different positions around Andromeda Center. Individual star systems that were used as navigation targets would have moved by measurable amounts because of their own orbits inside the galaxy. The travelers would arrive at a destination that had aged past what their instruments and maps could recognize. They would carry charts of a galaxy that no longer existed in that form. And all of this assumes a level of technology so far beyond anything humanity now has that talking about it in practical terms is almost fantasy. We have not sent a crewed mission past the moon. We have not kept a person in space for longer than about 437 days in a row, the record set by Valery Polyakov aboard the Mir space station. We have no experience with closed-loop life support systems for more than a few years. We have no propulsion system that can speed up a crewed vehicle to even 1% of light speed, let alone 99%. The gap between where human spaceflight technology actually is and where it would need to be to try an intergalactic crossing is not a gap of decades or centuries of progress. It is a gap of size level so large that the word progress stops meaning anything. Generation ships, a popular idea in science fiction, offer a partial way around the problem. Instead of needing individual humans to survive the whole trip, a generation ship would carry a self-supporting population that has children over thousands or millions of years, with descendants finally reaching the destination. The original passengers accept that they will never see the destination. Their job is to start the trip and keep the ship working long enough for future generations to continue it. The idea has a romantic feel. It turns the trip from a test of one-person endurance into a shared civilizational project across evolution-sized timescales. But the practical problems are almost the same as impossibility when applied to the distance to Andromeda. At 10% of light speed, the most optimistically fast generation ship would need to keep a working population alive for 25 million years. Think about what that takes. A closed ecosystem that can recycle all water, air, and nutrients without any outside supply for 25 million years. A social structure stable enough to keep a shared purpose across about 1 million human generations. A technical system that can repair itself and adapt over timescales longer than most species last on Earth. Materials that do not break down over millions of years of constant use in the harsh radiation of intergalactic space. Every single part of the ship, from hull plating to air filters to food production to genetic diversity management, would need to work without deadly failure for a period longer than the whole history of the genus Homo by a factor of more than 80. No material we have ever made would last that long. No social structure we have ever built has continued for more than a few thousand years, and most fall apart in centuries. No ecosystem we have ever seen, natural or man-made, has worked as a closed loop without outside energy and material inputs for more than short experimental periods. The generation ship idea applied to intergalactic distances is not a hard engineering problem. It is a category mistake. It takes tools meant for interstellar distances where trips might be decades or centuries, and tries to use them for intergalactic distances where trips are millions of years. The two problems are not on the same scale. They are separated by the same kind of quality gap that separates swimming across a river from swimming across an ocean. This leads to the hardest truth in this whole story. The distance to Andromeda is not just a big number. It is a physical limit. Not a wall in the literal sense, not a barrier made of matter or energy, but something more basic. A limit set by the shape of space, the speed of light, the energy needed to speed up, and the biological limits of every known form of life. Within known physics, the intergalactic void between the Milky Way and Andromeda is a permanent separation for any biological civilization stuck with slower-than-light travel. Permanent. Not temporarily out of reach, not waiting for some future technical breakthrough. Permanently out of reach within any time period that a biological species, a culture, a continuing line of technical development could realistically keep going. This is not a statement about human ambition or human intelligence. It is a statement about how the universe is built. The cosmos made its structures on scales that do not allow biological travel between galaxies. The same laws of physics that let stars form, planets come together, and life evolve also set speed limits, energy limits, and distance scales that keep any civilization born inside a galaxy inside that galaxy. The Milky Way is not a launching pad for intergalactic exploration. It is, for all practical purposes within known physics, the whole reachable universe for any species that lives here. Even inside the Milky Way, the distances are huge. The nearest star is 4.25 light-years away. The galaxy is 100,000 light-years across. A civilization that mastered interstellar travel at 10% of light speed could explore a large part of the Milky Way over millions of years, spreading itself across thousands of star systems, building a galactic network of amazing scope. But the step from inside the galaxy to between galaxies is not a step. It is a chasm. The distance to Andromeda is 25 times the diameter of the whole Milky Way. It means crossing 2.5 million light-years of empty space with no stars to visit along the way, no resources to collect, no gravity assists to use, no intermediate stops to rest or resupply. It is the longest, emptiest, most resource-bare crossing you can imagine, and it has to be done in one unbroken trip lasting millions of years. If an ant stood on a marble in the middle of a huge empty desert, and you told it that another marble was somewhere in the desert several miles away with nothing but flat sand between them, the ant could understand the direction. It could even start walking. But the distance between the marble it stands on and the marble it cannot see would be so far beyond anything the ant can do that the trip would be meaningless. The ant would die before covering a tiny fraction of the distance. Its descendants, if they could somehow continue the walk, would face the same limit. The desert is simply too wide for the creature trying to cross it. Not because the ant is broken, not because the desert is mean, but because the scale of one does not match the abilities of the other. That is the relationship between human civilization and the distance to Andromeda. The scale of the universe does not match the biological, energy, and time abilities of any known form of life. This is not a failure of imagination. It is a measured, counted, proven physical limit. And yet, go outside on a clear autumn night. Look toward the constellation Andromeda. Find the faint smudge of light that old astronomers thought was a local cloud of gas. Hold your eyes there. What you are looking at is the combined glow of 1 trillion stars burning across a disk of space 220,000 light-years wide, located 2.5 million light-years from your eyes. The light entering your retina tonight left that galaxy before your species existed. It has been traveling through the intergalactic void for longer than the whole evolutionary history of human intelligence. And now, it is ending its trip on the surface of your eye, turned into an electrical signal by cells in your retina, sent through your optic nerve, and processed by a brain that weighs 3 pounds and runs on about 20 watts of power. You cannot go there. No technology you will ever likely build can take you there. The distance is too big, the time is too long, the energy is too great, the biology is too weak. Andromeda will always be out of physical reach for any human civilization, and probably any living thing that will ever exist in the Milky Way. But you can see it, you can measure it, you can calculate its mass, count its stars, map its spiral arms, find its central black hole, measure its speed, predict its path, model its future gravitational meeting with your home galaxy. You can do all of this from the surface of one planet orbiting one average star in the quiet suburbs of a galaxy that is, by measurable standards, the smaller sibling of the pair. The Milky Way has between 200 billion and 400 billion stars. Current estimates say it holds somewhere between 100 billion and 300 billion planets, a large fraction of them orbiting in the habitable zones of their stars, where conditions might allow liquid water on their surfaces. This single galaxy, the one we are stuck in, gives us a cosmic territory so huge that a civilization moving at 10% of light speed would need 1 million years to cross it from edge to edge. No species that has ever lived on Earth has lasted for 1 million continuous years of technical civilization. The Milky Way alone has more space, more stars, more planets, more possible destinations, more unanswered questions, and more undiscovered worlds than any one civilization could use up in the whole remaining life of the sun. We are not locked in a prison. We are kept inside an arena of almost limitless possibility that we have barely started to explore. Andromeda, the giant next door, doubles that territory. But it doubles it across a gap that physics will not let biology cross. This is the real truth about our size in the universe. Not that we are small, though we are unbelievably, measurably, provably small. The real truth is that we are small enough to be permanently stuck in one galaxy among trillions, yet capable enough to measure the one next door with amazing accuracy. We can see what we cannot reach. We can calculate what we cannot cross. We can map structures so vast that no trip within known physics could ever go through them. And we can do it from a room, with a telescope, with math, with the same 3-pound brain that once tracked antelope across the savannah. You are 3 pounds of nerve tissue running on the food energy of a dim light bulb. You live for 80 years on a planet 7,918 miles across, orbiting a star that is one of 400 billion in a galaxy that is the smaller of 2 gravity-bound spirals separated by 2.5 million light-years of empty space. And you measured all of it. The scale is frightening. The distances are permanent. The isolation is real. But so is the measurement. And there is something in that fact, something exact and unstoppable, that no amount of cosmic distance can take away.